Can we start?
Yes.
I hope you can hear me. Okay, excellent. Okay, today we are going to move to, I don't know, maybe not more complicated, but the components that their behavior is connected not only by the electrical properties, but also by some optoelectronics components. So this is probably the last lecture about simple components. Next time we will go to the more complicated elements. So this is probably the last time we are talking about the basic components. Okay. So as I said, today we are going to the optoelectronic, the basis components of these parts are the diodes, laser diodes, LED emitting diodes, photoresistors, photodiodes, phototransistor, and so on. So we will be talking about them. And at the end, we will be talking about the photovoltaic panels, about the construction, principles of operation, characteristics, and parameters. But before we start talking about the electronic components, optoelectronic components, we must define what is the opto. Okay, so as we know, the electromagnetic spectrum is very wide. Yes, it starts from the long wave, the broadcast wave, and ends with the X-rays, cosmic rays. Yes. So as we can see, this is very wide. Frequency is very wide, long wave difference between these electromagnetic components that are about, let's start with 100 Hertz and stop with the terahertz and more. Okay, so where we are in our light, with our opto, as we said, we are very narrow band. This is the electromagnetic waves that our eyes can absorb, can detect. Is a matter of fact, you know, that we can detect red, blue, and green. Yeah. So it's a mixture of these elements. We can say it's everything about our colors that are surrounding us. So we are in the very narrow spectrum of electromagnetic fields. Yeah. Starts with more or less 700 and stopped 400 nanometers. Yeah, this is the wavelength of the electromagnetic. Below, we've got infrared that we, as a human being, can't see, but maybe some animals can see, and the ultraviolet. This is more than violet, so shorter waves than the violet one, and probably none of the human or animals can see this electromagnetic fields. Okay, so our properties of the optoelectronics come from infrared, visible light, and the ultraviolet. So this is our opto, yes, in our optoelectronic devices. We do not utilize the microwaves or broadcast band and the radio frequencies, electromagnetic spectrum, nor the X-ray and gamma rays. Okay, so as I said, our visible light visible light ranges, as I said, from 700 nanometer to 400 nanometer. Okay, so this is our visible light, what we can see. Okay, so as you can see, we've got different colors: violet, blue, green, yellow, oranges, and the red, of course, and infrared below, and ultraviolet shorter waves. There are some bands that describes the colors. Of course, they are not exactly, but more or less. As women said, men can see colors. So I'm not going to tell about colors at this time. Okay, so why we can see the colors? Well, no, it's not a problem. But how it is generated, the color, or how the electromagnetic field comes from? As we know, we can see because we've got a light surrounding us. So generally, the electromagnetic fields that allow us to see things comes from the sun, okay, or other sources of light. Yes. So we need a source of light to see the colors. Yes, we can't generate the source ourselves, so the substances, the things must reflect or emit some electromagnetic fields in these frequencies. Okay, so, and then we can see the color. Okay, but we need to, in a matter of fact, describe this fact. Okay, the Stefan Boltzmann found that the objects reflect the electromagnetic energy, so they emit the electromagnetic fields when they are warmer than absolute zero. So it was the black substances, like black box, never mind. But he noticed that if we have the temperature of the device of this black box greater than zero, it's emit the electromagnetic radiation. And the amount of this emitting energy is dependent of the temperature. If the temperature is higher, then the object reflects more energy. Okay, so this is can be seen if we hit some metal elements, and then it starts to be red and then yellow or something. Yes, so if we warm some, of course we must warm more than 100 Celsius degrees, because we can see this infrared waves. But if we make it 1000 Celsius, so we can see that the metals, for example, can emit some energy, and we can see they becomes red. Okay. So this is the Stefan Boltzmann law, and it gives us a theory that the total energy that emits of the black body, is made by this equation. Yes, so we've got the total energy emitted from the surface of the black box, and this is the Stefan Boltzmann constant, and this is of course the temperature of the black body. Okay, and this caused that I can show you the slide. Okay, and the classical this classical theory, the Boltzmann theory, said this is this is more temperature, we have higher energy, and high energy corresponds to the energy of wave length, and if more energy, the wavelength is shorter. So we've got shorter waves in the black box, this black body. Okay, so that was the Stefan Boltzmann theory, but it doesn't explain everything. So the physicists thought about the problem, and it was a Planck who discovered some different theory of the black body, black box radiation. He said that it could be an oscillator, because if we know, can you hear me? Because I'm.
Yes, we can.
Okay, thank you. You can see then one node. Yes.
Yes.
Okay, thanks. Is only one student on this lecture?
No, there's two.
Oh, two. Oh, yeah.
At least three.
3. Okay. Okay. I hope it's more than 3. The Planck. We've got the Planck. And this is the physicist who discovered that the total energy of the black body, black surface, is connected with the energy of kinetic. So this is the kinetic, depends on the movement, and the potential energy. Yes, so we know it's from mechanical theory of energy. Yeah, and we know that we've got an atoms in the substances, so they are shaking, they are moving, and these energies are connected with this movement. One is connected with the temperature, one is connected with the frequency of the oscillation. So in this case, you can say that this is similar to the mechanic one, and this of course omega is the frequency. Yes, this is the frequency of oscillation, because atoms shake. Yeah, they are shaking, so we've got some oscillation in atoms. So this is the oscillation of the. This is of course the mass. This is the mass of atom, of course, because we've got different energies for different substances. And P and Q are the coordinates So this is where it exactly is, that's the atom. Okay, so if we change this equation, we can see that if we set that okay, first we can change. If we set that the A is equal to B is equal okay, so if we convert this equation of energy into this one, we can see that this is equation of ellipse. Yes, this is an elliptic equation. And if we are, so we've got the ellipse. So if we calculate the shadow of the ellipse, we can say that the PAB is equal to this is energy and the frequency. This is the frequency. This is that was the frequency, but oscillation. So this is the frequency in hertz. So that was in omega. That is in this is in omega, and this is the frequency. So this is the hertz. Okay, and in this, so we can see that the corresponds to the position and to the frequency. Yeah, but this is constant for all the materials. Yeah, this is constant, and this is the Planck constant. Yeah, so this is the very important constant. Yes, this is the Planck constant. And if we can, of course, calculate this, we can also, using some experiments, we can describe that this constant is equal, okay, more or less joule seconds. Yeah. So this is very important constants because we can correspond to the energy of everything, of atom, of wavelength, of electromagnetic fields. Everything behaves similar. So we can describe that the energy of the, let's say, electromagnetic field is equal to the, or more detail, it's not an electromagnetic field, but the photon, because if you can see, the electromagnetic fields can be both a wave or the mass. So if the electromagnetic field changes from the electromagnetic fields to the mass, to the photons, and photons to the electromagnetic fields. So this is the dual theory of light. So the energy of photon energy, yeah, is equal to the Planck constants multiplied by its frequency, the frequency of the light, yes, of the electromagnetic field. And this is very important equation to understand what are going on in our electromagnetic fields. Okay, so do memorize this equation, do memorize that this is the photon can have the energy equal the constants, the Planck constants multiplied by the frequency of the light, yes, frequency of the electromagnetic field, which can be moved into the mass and the photon energy. Okay, so this is the theory that connects mass theory and the electromagnetic theory, wavelength theory. Yeah, so moves photons into electromagnetic and electromagnetic into photons. Okay. Okay, so if we can move to the presentation. Okay, this is what I wrote on the table, and this goes that our meaning of understanding of what happened in the black body radiation is a bit different. Okay, so we have okay, wait a moment, because I had some. Okay, this is a simple application that say how it behaves. Okay, so this is, we can set the temperature of the black body of the black box. Okay, and changing the temperature, we can see that we've got different wavelengths of the during the radiation of the black body. Yes, so increasing the temperature. First, we have the red wavelengths that we can see because we can't see the infrared, yes, and ultraviolet elements. Yes, this is the part of the body, the part of the electromagnetic fields that we can see. Okay, and increasing the temperature, we are moving towards yellow and then towards green and blue wavelengths. And this is also very interesting for you, because sometimes you are going to the shop and you have the bulb, the light bulb that they said someone is warm, something is LED light daylight, something is cool. So what does it mean? That this is this. If we got the bulb on 5,000 of Kelvin, so it corresponds to the emitting of the black body. If we hit the black body up to 500 Kelvins, we've got such a emission of the wavelength. Yes, this is the emission of the black body. So it's going more towards green and blue. Okay, and if we got the bulb in the, let's say 3007, so you've got something which is more towards red, so more towards yellow one. Okay, so it's more like a sunset. Okay, so this is what we have during the day, and this is what we've got during the sunset. Of course, it is not because the sun changes the temperature, but our Earth is moving, so changing our atmosphere. Yeah, so this is why. But if someone is asked to explain why we use the Kelvin to explain the light color, so now you know that it is the Planck theory, which can describe the energy from the body of the different temperatures. Okay, do you understand this? This is okay.
Yes, but can I ask a question about this equation from earlier?
Yeah.
Because I don't know if we need to know this, but these
No.
coordinates P and Q, I'm not sure what are they. How are those coordinates?
Yeah, they are the, this is the P and Q are the coordinates. So this is the coordinates of this ellipse. Yeah, so this is not any physical issue. So this is just a theory. This is just mathematics. But of course, you do not have to know this equation. But if someone is going towards physics, can study this problem more deeply, because there are thousands of articles about this problem. Maybe I'm not the best to explain this more deeply. Okay, so this is the most important for you is the Planck constant. Yes, I was trying to show you how it's
okay.
What is from, but maybe if anyone is more toward the physics, that can show us maybe in some slides. But I'm not the physicist, so maybe I don't understand what this equation means, but this is just a mathematical formula. Okay. Okay, so we've got the different temperatures of the black body and the different materials. Okay, so this is the theory. Okay, now, okay, we can also calculate, having this constants, we can calculate the energy of radiation, or in the opposite way, having the energy, we can calculate the frequency. Okay, so this is, if we've got, this is the example that we've got. Yeah, this is the Planck constants for red light. So for red light, we can say that it is this wave. So we can calculate the frequency of red light is 492 terahertz. Yeah, and it has an energy of this. Yeah. And more that we've got 1 mole of photons, we can calculate the total energy of the mole of light. You can say a mole here, because this is the problem, that we do not know when it's the photon and when it's a wavelength. So this is my electromagnetic field, or this is the mass. Okay, but we can calculate some, having this Planck constants, we can calculate different elements of this radiation. Okay, so let's start. I don't know, it's the easiest one, but maybe not the easiest, but it corresponds to the above theories. We've got, you know, that we've got lasers in our environment, maybe not environment, but in our devices we use. Yes, but what is the laser in the matter of fact? Laser is a name. It means light amplification by stimulation emission of radiation. So we've got the two physics things. One is the light amplification. The second one is stimulated emission. Okay, so we should explain what's going on. Okay, so we can move to the. Okay, where is my note? Okay, here it is. Okay, so we know this. Okay. There is also another interesting problem. If we've got atom, oh, this is the, and we've got electrons. This is the Bohr model, but never mind. We can use Bohr model. Okay, we've got electrons on the last shell, but it was observed that in some circumstances, these electrons can move to a different shells. Yeah, so these electrons can jump here because everything is shaking, and if the atom has enough energy, of course not all substances, but some substances, some atoms can jump from one shell to the another. Okay, this is of course made by some energy from outside. Yes, so we've got the energy, or the heating, or the light, or the electromagnetic, or electric, never mind. We can somehow move the electrons from one orbit to the another orbit, one shell to the another shell. But is it stable? No. In some substances, it causes that this is the not stable position, and it jumps back, yes, to the proper. And this energy, of course, is equal this energy. This energy we move to the atom is equal to the constant, Planck constant, and the frequency, yeah, because we have some emitting energy. Yeah. So the energy is emitting, and this, of course, this emitting energy is equal to the energy that was necessary to move this electron from one position to another, and this energy emitting is equal to the constant and the frequency. If so, we've got two physical behaviors. One is the moving the electrons to the upper position. Yeah, we can say this is absorption. This is the absorption, and moving from one position, from higher position to the lower position, we've got the absorption, so some energy from outside, yeah, and we've got the emission. We've got the emission to the outside world, yes. So, if the energy, which is equal, is, so we can say that the frequency, yes, is equal energy divided by Planck constant. Okay, if the energy is enough to have the frequencies that corresponds to our colors, so we can have the emission of the light. Yeah, of course, from infrared to ultraviolet. Yes, this is the band we do utilize today. Okay, so we need to have a special energy, or we need a special atoms that have these properties. Yes, that when the electrons goes from the higher orbit to the lower orbit, it emits a quantum of energy, which is correlated with the frequency. Okay, so if we remember that for the red light, we've got the frequency, I don't remember, 400, or more or less 400 terahertz. Okay, so we need an energy, yes, a special energy, quantum of energy that corresponds to this frequency. Okay, so if we got such an atom, we can make we can move an electrons to the higher energy, and when it goes back, it emits an energy as an emission, as an electromagnetic emission. Okay, so that was the absorption. This is the absorption and emission. Yeah. This is the one part of the, and another one problem is the stimulation. This is another part of the word laser. So stimulation emission. Okay, what does it mean? It means that if we've got this similar situation, so we've got maybe we've got two atoms. Yeah, it's the simplest. Yeah, so we've got two atoms. both of them have the absorption. So somehow we put the energy to the atom, the quantum of energy, of course, and the electrons goes to the orbit. Okay, as I said, it could be stable or metastable, because in the atoms used for substances used to produce the lasers, we've got the atoms that have some metastable position. Okay, so the electrons can be here, but can also jump to the lower energy. Okay, so if we pump, this absorption. Yes, using this absorption is called pumping. Pumping. We pumps the atoms. Yeah, we pumps them. So we are changing the energy of the electrons. Okay, so we are pumping to the higher shield, to the higher layer. Okay, but as we said, it's not stable position. So this electrons can jump. No, it emits the energy. Yeah, equals, and it comes. This energy comes towards these electrons, and this energy can cause that also can cause that the electrons, if it is stable position, this energy can cause that the electrons jump to the lower energy, so it emits also the energy. But we've got also this one, so we've got two photons, two parts of the stimulation emission. Yeah, this is both electromagnetic field and the photons. Yeah, so if you can see, if you got pumping more and more atoms, we can have more and more light. In our case, yes, more quantum of energy. Yes, so if we have more atoms, more light. So this is the stimulated emission. It's not so easy in real life, because, as I said, there are not many substances that have one layer that is stable, yes, semi-stable, stable. Because if we are pumping, we would like to stay these electrons on the higher orbit. But there are different substances, different correlation between substances, and this is one layer. But we can also have some atoms that we can jump. Yes, this is the base energy, but then you have, for example, two layers. And if we move some energy, yes, to jump these electrons to the higher orbit, yes, and this is easier for us, for example, because we can use different energy, different wavelength or something like that. So the atoms goes to this orbit and it goes back. Of course, it emits some energy, but the frequency are above or below what we know. Generally, there are shorter wavelengths or higher frequencies, so this we can't see it because it's over violet. And this is the stable position. And to move these electrons from this position to this, we need some light, some stimulation outside light. Okay, so this light causes drop down. So, and we've got two signals to stimulation emissions. Okay, so as we can see, because we've got the waves and the same energy, so it means the same frequency. So the laser light is monochromatic, more or less, of course. Okay, so we expect that if we got this electromagnetic, that for red light we've got only just one peak. Yes, this is or lambda equals more or less 400 nanometers. Okay, so this should be what should we know about the light emission. So we know that is the monochromatic. Okay, and something, don't know what is coherent. It's also coherent. Why? Because this stimulation energy comes, which causes the drop down of the electrons, is in the same phase of the energy what was from this electron. Okay, so it is the coherent. So it's got monochromatic and coherent. Okay, but this is the idea, but in our this is the linear, yes, but in our real life we have, of course, different. This is the atoms, yeah. We do not have atoms in line. So if we pump them, if we move the electrons to the higher orbit, they start to emit. But we don't know on which way what is the direction of the emission. One could start this one. Yes, one could stay on this one could on this. Of course, we've got a lot of atoms here. So this atom can, for example, emit also this one, then can move here and emits. So we've got two here. Yeah, this can, I don't know. Yeah, so we've got this situation, and this is not a very nice situation because the light goes around of us. So as you remember, the laser we utilize is a very narrow wide stream of light. Yes, so it doesn't work in this way. So what to do to make the laser lighting in the one direction? We can, okay, we still have this atoms that are pumping, yeah. And some of them make this direction, but some of them makes this direction. Yes. Okay. Okay. So we can add some mirrors. we can add some mirrors. Okay, that's green. If you add the mirror here and the mirror here, now this quantum of energy goes to this electron. Yes, it goes further two. Yes, so two of them will mirror, so they are on this way, and they are go back. Yeah, and they can find, for example, this atom. So we've got, yeah, they found this, so we've got three of them. Yeah, and goes to the mirror, and again. Yeah, so, but the atoms that emits the light in wrong direction, they disappear. Yeah, if this, because we have no mirror here. So if we use two mirrors, we can utilize that the light emission will be in one direction. Okay, this is in typical, one mirror is the full mirror, one mirror is the part mirror. So if you've got a lot of, or a hole here, so if we have enough energy to come, so the photons will go through this semi-mirror element, and it goes on this direction. Of course, if you can see, they are in the same phase, so they coherent, they are monochromatic, and they are in the one direction. So are they collimated. Collimated. So we know. So then we know that laser has the light that is monochromatic, coherent, and collimated. Okay. Okay. As I said, there are. Okay, we can move towards the. Okay. So we've got, this is obviously okay. So as I said, we've got different substances that we can utilize to produce the laser. Generally, we can have solid substances, liquid substances, or gas. So the first laser was made of this was the gas laser. It was the mixture of helium and neon. And why they use a mixture of neon and helium? Yeah, this is the explanation. We've got the helium atoms that we can pump by electron collision. So we've got an electric fields outside of the bulb with the helium and neon gas, and we can pump the helium atoms by an electron collision. Yeah, so we move the electrons from zero orbit to the S0, S1. Okay, and by collision of the helium and neon atoms, we move the neon electrons toward S3, S5, and S4 layer. Yes, and there are also the semi-stable, as I said before, and as you can see, the electrons from the S5 can move to the P4 by emitting electromagnetic fields, but 3 micrometers, but it is outside because it's near X waves. So this is below infrared, okay? And this This frequency is what we know. This is the green one. Okay. So if the electrons goes from the 5s to the 3p, it corresponds to the energy we can achieve. Yeah, and then it goes lower, yes, to the 0. Okay. So using these two atoms, we enable to move the electrons from the 0 to the orbit that gives us the frequency we expected. Okay. Yes. So as I said, we've got different substances. First of all, it was the gas helium neon. Another was the ruby laser. This is the solid state material, solid state lasers. The ruby gives us red light. We've got some liquid substances and so on. Okay, so what I said, it is necessary, of course, what substances we do use using the laser, but another one is the element, the mirrors. Yes. We've got a different kind of mirrors. This is the parallel resonance of the parallel mirror. Of course, it is important what are the distance between the mirrors, because if we should achieve some resonance, because otherwise the elements can, yes, because if we, yes, because the problem is that we've got these mirrors, and we know that the wave is, that the velocity of photon is not infinitive, but is also by light velocity. So we've got the wave, yes, which if we got it here, it's also goes back with the same frequency, yes. And the same situation is here. So if we have wrong distance between the mirrors, we can have the situation that the photons going from the one side and are in the different, if they are in different, so it means that we've got nothing, yes, because the photons will collide and we have no energy here. So we need to have the distance that makes the resonance, yes. So we have to achieve that yes, this is coming from one mirror, this is from this mirror, yes. So we should have the same phase, yes, from both mirrors. Yeah. And this is the distance which should be more or less divided by 2. Yes, because otherwise we have no energy, we have no light coming from the lights. Okay, so we've got the different yes, so this is the parallel, this is the synchronic, this is the confocal resonance. Okay, so we've got different I will show you a film that should explain something more about this problem. Yes. Can you see this light amplification?
Yes.
Okay.
We want to create an avalanche effect, where the spontaneously emitted photon that was created when an electron transitioned from the metastable state to the ground state gets amplified through the means of stimulated emission. We don't want just a single puny photon, we want lots, all working together. It is not practical to create a laser that is extremely long, so the solution is to put the laser medium in a cavity. let's take a closer look at how our cavity will influence the light waves, and how exactly this will create the amplification we desire. Since light is a wave, it will be subject to constructive and destructive interference. We want constructive interference in our cavity to take place, in order to have a high-intensity beam. A laser cavity has a mirror on one side and a partial mirror on the other. It is partial because we want some of the beam to escape. That's the beam we see. Now, when light waves are created through spontaneous emission, they will initially travel in random directions. But the ones traveling perpendicular to the mirrors will reflect back and forth. Let's take a look at one of these light waves. It is first emitted via spontaneous emission and quickly becomes large in amplitude through stimulated emission. It travels towards the mirror and is reflected back. Because we continue to stimulate atoms in the left and right directions, we get two waves in the cavity. Again, one moving to the left and one moving to the right. Waves will add their amplitudes when interfering with each other. In this case, we will get a standing wave. Meaning instead of a wave noticeably moving to the left or right, the combined wave will appear to be going up and down. Rest assured, this is just an illusion. This is the effect of two waves hitting each other head-on, and their left and right components cancel out, but their up and down components add together. So when the wave looks flat, this is a moment when the two waves are destructively interfering with each other, and at the maximum they are in a constructive interference point. Here are a few examples of some standing waves in a cavity that are resonating. Resonance is just a fancy word for having these waves being in a state where standing waves are being produced. A mode being just what n you have. N equals 1 is a mode, n equals 2 is another one, n equals 3, etc. Is there an equation that will tell us what modes can exist in the cavity? Sure there is. The left part is the frequency that exists in the cavity. N is the mode, which is always an integer. V is the velocity of the wave, and L is the distance between the two sides of the cavity. The velocity in our equation is the speed of light, c, which is 300,000 kilometers per second. The L is just the distance between the mirrors. Light traveling from the left of the cavity will now interfere with light traveling from the right. So again, we have these possible modes where the light can produce standing waves and be in resonance. Not all frequencies are able to exist in a cavity, but a lot are. Also, let's be clear that the standing waves produces are a collection of trillions and trillions of light waves all working together. They are produced by stimulated emission, and the cavity allows them to keep amplifying each other. They are coherent with each other. Recall, this was one of the big reasons why we care about lasers. If we didn't have this synergy between light waves, we would just have an ugly LED. I bet you can't make your cat go crazy with a red LED. Well, maybe, but you get my point. Question: what frequencies are allowed to exist in a red laser pointer's cavity? Answer: a cheap red laser pointer has a cavity length of about 1 millimeter, and the speed of light is c, 300 million meters per second. Plugging in these values to our equation, we would get a difference between allowed frequencies of about 150 gigahertz. Now, red light has a frequency of about 400.05 terahertz, which corresponds to an n value of 2667. Recall n must be an integer. So if 400.05 terahertz is an allowed frequency, then the next one would be when n equals 2668, which is a frequency of 400.2 terahertz. We can plot all allowed frequencies, as we know 150 gigahertz will separate them. The plot will look like this. Here we have n equal to 2667, and the corresponding frequency of 400.05 terahertz. Here is 2668, 2669, and so on. These are the frequencies that are allowed to resonate in this laser cavity. So if you wanted your laser to have a frequency of 400.1 terahertz, you would first have to change the cavity length for this to be allowed, as it is not possible in this red laser's cavity. About 2,600 frequencies in the visible spectrum would be able to resonate in this red laser's cavity. Now, there is slightly more to the story about these allowed frequency lines. We have assumed the mirrors are perfect, which is practically impossible. The imperfectness of the mirrors and other slight variations add a thickness to the frequency lines. The actual allowed frequencies in a laser cavity looks like this. Again, this is due to imperfections. The last piece of the puzzle is to mention the gain medium itself. Gain medium is just the material we are using for our laser. Different materials will have different energy levels. Hence, photons of different energy will be released during stimulated emission. For example, different materials will need to be used to create a blue laser than that of a red laser. Since the energy levels in a material are discrete, one would think that exactly one frequency would be emitted out of a laser, but only if this is also a frequency allowed in our laser cavity. We can superimpose these ideas on this graph. We assume here that indeed the stimulated emitted photon is a frequency that is allowed in the cavity. However, there is much more to the story. The frequencies being emitted out of the laser actually takes a shape like this. This was briefly mentioned at the beginning of this video when discussing line width. What is going on here are complicated events such as the Doppler effect, Stark effect, and other quantum mechanical behavior. The takeaway is that the gain medium does output a small range of frequencies, and has this gain curve. It is still extremely narrow, and said to be monochromatic. It's not, but it's close enough. To sum up, certain frequencies are allowed to exist in a laser cavity. There is some relaxation to these frequencies as the mirrors and such are not perfect. The laser gain medium emits photons in a certain frequency as well, but again there is some broadness to this as certain effects influence this. We can superimpose these two frequency plots and get the following. The frequencies under the gain curve that have enough intensity to overcome other cavity losses are the ones the laser emits. There are plenty of laser active medium these days. Any frequency you wish to lace is pretty much possible. Here is a picture of different laser material, and the frequency they output. Some are in the gas state, some solid, and it is even possible to use a liquid as a lacing material. This concludes this episode on the laser. If you enjoyed the
Okay, so as you can see, the resonance number of resonation waves is also important to produce the proper light, proper laser light. On the example, we could see that the 1 millimeter of distance between the mirrors causes that we've got a lot of different frequencies, because the frequencies that could be multiplied in this situation are in the 150 gigahertz, as I remember, distance. So we can have different frequencies, and is a matter of fact going from the laser. As it was said on the film, it is very difficult process and different physical things going on in this situation. This is the simplest, probably the simplest equation. What's going on in the lasers process, the light, but you do not have to remember it by memory, of course. So generally, the problem is that the wavelength going from the laser is not only the one frequency. Yes, so this is the Gaussian curve that shows us that we've got different frequencies in the going from the laser. Of course, if you get a smaller number of n, yes, which corresponds, if we've got a smaller n, we've got a better laser, but the distance can't be nanometers, yes, because it's not physically, it's not practically to achieve, because it's very short distance. So what we can have achieved is 0.1 millimeter or something like that. So, but increasing the number, we increase also this Gaussian curve, yes. So we've got different frequencies going from the laser. Okay. Because the laser theory starts from the 60s, then we had only just the lasers for the scientific, and then today we've got the integration age, so the lasers are everywhere. So this is the how many. This is the from the 10 years graph, so we know how many lasers are used for different categories. Can we see that a lot of them are used for healthcare sensor or healthcare lasers, and some telecommunications, some elements. So we have the lasers nowadays everywhere. Okay. Okay. So that was the proper laser. Yes, this is the laser as a theory. Of course, the laser is very good because it has a very good properties, but in our case it's very difficult to utilize because it needs the pumping, it needs the mirrors, it's a lot of things. It needs some temperatures because sometimes it works only in lower temperatures. So it was not very common element, especially the gas laser. So what we are going to, it's the emitting a light, emitting a different light by electric properties only. Yes, this is the solution for electronics because we've got electric energy everywhere. So we're talking about diodes. Yes, that was the PN junction element, so the elements which connects with the donated silicon donated and with one with electrons, one with holes. Yes, so it was shown that if we combine also such a layer, such a sandwich with PN, and we can also have an element which emits light. Yes, so we can make a light emitting diode using the PN junction. Of course, the problem is the substances, because as you remember in our PN substances, yes, N with electrons, P with the holes. If we add some energy, the holes, the electrons goes to the circuit. Okay, but they jump. We can say that the electrons jump to the lower energy, and the electrons can combine with the holes. Yes, because it's also the atom. And if the energy needs to allows the electrons goes to the lower layer and connect with the atom with holes. If the energy is equal to the energy for frequencies, visible frequencies, yes, the light frequencies, we can expect that the collision, the combination of the holes with the electrons gives us a spontaneous emission. Yes, and we can achieve some light emission. Yes. So this process called recombination. Yes, the recombination needs to have the proper energy for different wavelengths. Yes, for different scales. So we've got two possibilities. One is direct recombination, that we've got this energy, this band energy. This is minimum energy for the conduction band lies directly above the maximum of energy above the valence band of the momentum space in direct band gap materials. This means that the band energy is equal to the energy for these substances. And this energy is enough to move the electrons and to recombinate with the holes and to emit the light. Okay, and this is, for example, for arsenic gall. This is the example of the substances that the emission, that the band gap, yes, the energy of the band gap is similar to the emission for the visible light. Yes, and this is the direct, so the electrons recombinate with the holes, and we've got emission of the light of the electromagnetic field. And another solution is the indirect recombination. So the energy is enough to move the electrons toward higher orbit, and then when it goes low, it causes the light emission. Yes, this is this situation. So the energy moves to the higher orbit, but it goes lower, and this causes the emission of the light. So this is an indirect recombination, and this is for different substances. For example, this is the example of the indirect recombination substances in the PN and N substances. Okay. So this is the principle. This is the principle of operation. Of course, in our real life, the LED structure plays a crucial. The structure of this sandwich plays a crucial role in emitting light, because we need a very low layers, because the light must go out of this element. Okay, so we've got something like this. So we've got the P layer and two layers of N. To N layer, one is more donated to have a proper band gap of energy, which is equal to the special wavelength and the special color. So we've got this construction emits light everywhere. This could be smaller light emission. Okay, so this is the example of how can we construct the light diode. Okay, of course we can talk about the efficiency of light, because not all of the energy we put into the element move to the light emission. Yeah, because we've got some heating, we've got some resonance, we've got some elements. Some of them produce the electromagnetic field that we do not see, so it's outside of our vision. So we've got the index of efficiency. This is, of course, connected with the optical energy versus the energy we can put into the element. So this is the current multiplied by voltage, by the different of by volts. Yes, on these elements. Okay, we've got different, as I said, we've got different substances which can emit different colors, different wavelengths, starting from infrared and stopping with the ultraviolet. So we've got a lot of substances that are utilized to add to our P and N sandwich. Yes, and they then can light they can light different wavelength. Okay. As we said, we need a different, because we need a different energy to produce different wavelength. Generally, going from the Planck theory, if we've got higher frequencies or shorter wavelengths, we need more energy. So it should be also the same for the LED diodes. If we have lower energy, we should produce lower frequencies, high energy, high frequencies. Maybe we make an experiment. What's the time? Okay, we've got time. Can you see multisim?
Yes.
Okay, so we can prepare a small circuit. Let's say we start with the red one, okay? And we put a green one, okay? I would like to check the voltage current characteristic of these elements, okay? Because it's explain us what's going on. So we add some source of voltage. Generally the diodes, the photodiodes, I know that I up to 5 volts, for example. So we can change from, of course, it's different for different colors, but it's maximum, okay? So we will reconstruct two circuits, one for green one for red one. Okay, I hope it will work. Okay, so let's make a simulation. Second output. We need the, for example, voltage. We need some current. Why we don't have current? Gosh. Okay. Probably we can't see some. Okay, maybe different. It's too much voltage. Let's say okay, so if we can see, okay, something here. Okay, so you can see that we've got different, because we increase the voltage. Yes, this time corresponds to the increase of the voltage. We've got a different points when the LED diode starts to conduct. Yes. So if we can see that this green one corresponds to the red light diode. Yeah. So it's faster. It starts from 2 volts or something like that, and the green one starts later. Yes. So this should be like this because we need higher energies to produce a light with lower wavelength, yes, higher frequencies. So this is the characteristic of the LED diode, similar to the typical PN junction, but different from different substances because they have to emit a different frequency, the different energy of photons. Okay, so we check that is this true. So as we can see, if we can use different diodes, we can see that the forward voltage is lower for the infrared and higher for the blue and white diodes. Why the white diode is in this position? Because in many solution, the white doesn't come from the diode itself. The diode emits ultraviolet, and the ultraviolet with luminescence gave us the light, the white light. So we've got in the matter of fact, we've got two possibilities of to achieve white light. Okay, so maybe we should explain what is the white, because it's not easy, because we have no white color in physics at all, because it's not a special wavelength. Yes, so as I said on the beginning, we need a source of yes, like a sun or something like this. This is the source of electromagnetic field that allows us to see. In the matter of fact, if we've got this 700 to 400 nanometers, yeah, this is the band we can see anything. So we need a source of energy. We need a source of electromagnetic fields with this frequency. So the light generally gives us all of these frequencies. So we've got, it's combined of, we've got, we've got infrared, yeah, red, and so on. So generally, the white, of course, it's going back here. Okay, more. It's okay. This comes from the light. Okay, because not all frequencies, but a lot of them. but nearby our visible light, we've got infrared, yes, frequencies that gives us some heating. Yes, we can feel that the sun hits us, and some ultraviolet that is not also, that also we can see if we are on the sun for more time. So the white that comes from the sun is a mixture of different waves. Yes, this is a mixture of different frequencies. It's nearly the same amount of the light of the waves. Yes, so this mixture is combined with different frequencies, but the amount of these frequencies are nearly linear. Yeah? So we can see all the frequencies, all the colors. Yes? So we can say it's light. It's a white light for us. Yes, this is white. In our eyes, we've got, as I said before, 3 receptors: red, green, red. RGB, as we know, we can get the reception of this three frequencies. So if all of them are full, and so because we can sense some stages of this of the signal. Yes. Okay. If we've got the frequencies of red, yes, green, and blue, and they all full, yes, so we've got something. Yes, this is from the microcontroller. If we've got full 8 bits for the color, so we've got the full, we can see it's white. Yes. So in this means that we can have both only these 3 frequencies to see the white light, or we can have a full spectrum of frequencies. Okay, so there are 2 different white light emitting diode. One is connected with the red, green, and blue. Okay. Yes. So the mixture of red light and blue gives us white. Yeah, this is one concept. And another concept is that we've got one diode, which is ultraviolet, so this is the frequencies we can't see, and a white absorber. Yes, this is the substance that creates the white. So it creates different frequencies. R, G, B, but also another ones. Okay, violets. Okay, so this RGB white light emission produce only these 3 frequencies, which are sensed by us as a white, or we can use an ultraviolet diode and the luminophore to produce more frequency. Okay, in this case, we can change the warmth of the light. Yes, as we remember, the temperature of the light. Yes, because we can add some red, so it goes toward low temperature, or if we add some blue, we go towards higher temperatures. Okay, so we can tune the light warm, and here we can tune the warm. So this is, we can add some layer which produce warm or daylight. Okay. Yes. Any questions?
I suppose not.
Okay. Okay. I don't know. Yeah. Okay. Maybe we'll manage to finish it. Okay. So this is it. Okay. Another part of the light emitting elements is organic light emitting diodes. It's a different way of light emission. So this is the more complicated structure. Then we have a special emission layer, special substances. So the elements that are, this is the organic. Yes, this is conductor and emission layer. This is set as this is the kind of polymers, kind of organics elements. Yeah. So, and some elements that conduct the electricity, and in this way we can have the light emission. So this is organic light emission. Nowadays it's more in our cellular phones or television, so maybe it's more, we can use them because they have higher properties than the LED ones. Okay, this is some theories how it works. Okay, so that were the elements that produce the light. Yes, this is the, we have lasers, we have bulbs, we have LED emitting diodes, and now I would like shortly on maybe, okay, no, goes towards the elements that sense the light. If we know that we can produce an energy, maybe we can detect the energy. Yes, this is important question, because of course we can see the light, but we can sense the light, so we can't say it's the properties, some kind of, okay, we can say it's a color, we can name the color of the, but we can sense it directly. So we've got some elements that sense the light, sense the photon, sense this energy, and the simplest one is the photoresistor, known as a photodependence resistor. So as the name said, it is an element that changes the light, the resistivity of the element due to the light intensity. Okay, so we've got this is the light dependent resistor. So this is a special substances which changes the resistivity of the element due to the amount of outside energy. This depends on the wavelength, depends on the intensity, depends on the and other elements. Okay, so these elements are usually made with the sulfate of lead or the selenoid lead, so we can, or antimonium. So this is the substances that changes the resistive properties due to the amount of energy. So typically they sense the wavelengths between 600 and 500 nanometers. So this is the part of the visible spectrum, but it's enough to sense this. It's like this is the correlation between the resistance of this elements due to the illumination, to the amount of light energy. So if you can see that the resistivity is going lower. If we have more light, we have lower resistivity of the lower resistance of this element. If so, we can make a very simple circuit using the light emitting element and to add another resistor. So we've got something like a voltage divider. Yeah, this is the equation of this divider. So we've got the voltage signal, which depends on the light intensity. Yes, this is the simplest solution, simple element. But it's not only the one solution to sense the light intensity. Our PN junction, as we know, we can use a simple diode, we can use a photodiode, but we can also sense light, because if we can produce the light, maybe we can sense the light. So we expect that the light energy can cause something in this PN junction to sense somehow the amount of this light, amount of the energy. Okay, generally we've got four types of these elements, photodiodes. We've got simply PN junction, we've got PIN junction, avalanche, and Schottky diodes. They are all, we were talking about them as a typical diodes, but rectifier diodes, but we can also use them, but maybe not in the same situation. We can use them as a photodiode. Okay, so generally you remember the escape work. It is needed to escape the electrons out of the surface of this. If we correspond it to the Planck constants and the energy of photons, we need if we achieve this energy enough to escape the electrons out of the surface, we can say that we've got electric transition. So, of course, the escape work is different for different materials, different elements. The smaller work function easier for electrons to be emitted from the metal. Yeah, so the metal is easier to escape the elements. So we can produce some elements which change the resistance. Yes. So here we've got some elements which changes the resistance due to the light emitting on this. Okay. So if you remember, we had the light emission, so we need the electrons going from electron with collision with the holes. But in other way, we can say that if we got the light and some electrons on this on the p-doped element, yes, the light can cause the movement of electrons. Yes, because the energy can cause the jump of electrons in the higher position. Yes, so in this situation, we can say that in PN junction, we can make the conduction with the light. Yes, so the light causes the conduction, cause that the energy of light causes the electrons jump on the higher position and jump through this forbidden jump from the depletion layer. Yes, so if so, we can expect that if we make similar construction as a photodiode, yes, because in light emission diode is this. You remember it was the same, but the light was on the another way. So if we construct similar elements like in photo emission diode, we can expect that we got similar effects. Yeah. So the electrons, the light cause the movement of electrons are with, and we have the conduction of electricity. Yes. We've got different, of course, we've got different materials which have different properties. Yes, so we use them for different wavelengths. So generally, germanium are the wider, higher lower frequencies, higher wavelengths, and for visible light, as we can see, we can utilize silicon as we expected. Okay. So how it behaves, how the photodiode behaves? It behaves like a typical diode. Yes, if we had no light here, we could have this one. Yes, so this is the property of the. This is the property of typical diode. Okay, maybe I will make an experiment. No, or maybe not. Yes, so if we had no light, we have this, and we have this curve. If we have more light, yeah, we can see that we have more current going through the circuit. Yes, so this is the characteristic of the photodiode for the different emission of outside light emission. Okay, so it sends the light, and in this graph we can see two modes that we can utilize to measure the light, because we've got part of photovoltaic mode. Yes, so if we have no current, so the circuit is open, we can measure the voltages. Yes, we can measure the voltages here. Yes, so we can measure in photovoltaic mode on photodiode mode. So if the system is polarized in the minuses, yes, the changes of current corresponds to the amount of light. Yes, so we've got two modes: photodiode modes and photovoltaic modes. So if we increase the voltage, if we decrease the amount of current. Yes. So do remember that we've got photovoltaic and photodiode mode. So this is important to prepare a special circuit. I know that here we've got an element that we didn't discuss. This is the amplifier, but maybe we will return to these circuits on the next lesson, because next time probably we will have discussed the amplifiers. Okay, what else? We can have also phototransistor. Phototransistor is an element like a typical transistor, but we have no electrical input as a base. Similar to the photodiode, light causes the flow of electrons, so it causes the base emitter movement of electrons, and this cause that allows us the conduction between collector and emitter. Yes, so if we had such an element, we can use it as a sensing of light with some beta coefficient. Yes, so it's more sensitive than a typical PN junction, than the typical photodiode. Yes, and this is the correlation between voltage and the current. This is, as you can see, it is similar to the transistors with different beta, with different base current. Yes. So we have amount of energy going from the light here, and it corresponds to the amount of current going through the base emitter junctions. Okay, so we can also combine two photoelectric elements and produce something what is called optocoupler. Optocoupler is the element that is made of, in a matter of fact, two elements. One is the light emitting elements, and one is the photosensor. In this case, is phototransistor. So why do we use such an element? So the light starts lighting, and the sensor, the phototransistor, sense that we've got the signal. Okay, this is used to separate electrical separation for the different circuits, because, for example, we've got high voltages here and we don't want high voltages on this side. So if we switch, if we make, especially if we have use an, for example, microcontroller on one side and a huge motor on this side, and we would like to switch it on, it's better to make an optoelectronic isolation, and the optotransistor, optocoupler is the element we use for. So if we switch the light on, we switch the output element. Okay. Oh, I'm a bit tired, but we are finishing. We have time? Okay, we have time. Okay, so this is a photocoupler, and then we go towards solar cells. You probably know what is the solar cells. It is it works as a PN junction, as a big photodiode. Yes, because in the matter of fact, in the combination of the P and N materials in the different, of course, different construction, crystals, monocrystals or semicrystals. So we can different buffer of this elements. So we can produce different elements. Yes, this is the N-type silicon. So we've got, yes, P junction here and P layer here and N layer here, or opposite light. We can use this is a monocrystal elements. Yes, so we can produce a different kind of solar cells using the same situation as it was in the photodiode. Yeah. But what next? There are some theories on the next slides, but maybe it's not very important. Maybe it's more important to make an experiment. Okay, I have prepared something. Okay, here we've got simulation of the panel. So we've got this corresponds to the amount of light energy, and this corresponds on the output of the panel of the big photodiode in the matter of fact. So let's say we change this element into voltage, step voltage. Generally the PN junction, you know, it's 0.77 volts, so it's also for the photodiodes. Photo panels have a lot of photodiodes glued together, so the voltages are different. Generally, the voltages are up to 50 volts. And in 1 second. Display. Okay. So we can simulate the characteristic of this element. 1 second. We can see the voltage on V1. Okay, you can see the characteristic. Of course, it's not very well seen here, so we can move to the Excel. You can see the graph which corresponds to what we are talking about. So we've got the current going through the elements when we have some light on it. Okay, so this is the characteristic of the elements. Let's make maybe more of these circuits. And different value of light emission. Double this. Okay. And simulation. You can see that we've got different waves, we can plot them in the Excel. Okay, so if you can see, we've got different value of current. Depends on the light. Yes, more light, more current going through this photovoltaic cell. Okay, so what now? This is the characteristic of the characteristic of the cell. If we generally we've got the characteristic of the current going through the cells if we stay in this way, yes, in this part of this chart, we've got the characteristic of the photovoltaic cell is something like this, and for different light we've got the different characteristic. Low light, low current. So in this case, we've got some properties of this of the element of the photovoltaic cell, and this should be okay, sorry, I will find it in the presentation. Okay, so here we've got, because this is the characteristic of our photovoltaic cell, depends on the light. So you can find that we have some elements that we can measure. We can measure the short circuit current. Yes, this is if we short the circuit to the 0 volts, we've got the current. Yes, so this is the important for photovoltaic cells. We've got also open circuit voltage. Yes, so we've got the voltage when the circuit is open. It's different for different type of solar cells and different for different light, yes, emission outside. So it's also the element. We've got the reverse saturation current. It's maybe less important. We've got temperature coefficient. That is very important, because if we have higher temperature, we have lower efficiency. As you can see that here I've got some charts of the efficiency of the panel. So if we increase the temperature, we decrease the panel efficiency. And of course, we've got the parameter or normal module efficiency. Okay, so we've got some parameters that are distributed with the panel. So in the data sheet of the special element should be written this elements. Why we have this parameters very important? Because we need to achieve a higher efficiency of these elements. Yes, because we would like to make a better efficiency of this elements. Okay, what's the problem? The problem, yes, I wrote it here. The problem is here. So we've got the current, we've got the voltage. Where is the maximum P, which is I versus V max? Where is it? To find it out, we should multiply. Yes, we should multiply current and the voltage. Yes, so if I will try it here. So now we can. So no, it's the opposite way. It's because the current is in minuses. Okay, so never mind. It should be rotated. Yes, it should be up, and this should be down. So the higher efficiency is in this point. Yes, if we increase the voltage, we decrease the efficiency, the power of the element, and if we decrease the voltage, also we can decrease the efficiency of the power of the element. Yes, so we should find out the possibility to stay in this way, but it's different for different here. Maybe I will change to better. Okay, so similar here is equal.
Yes,
Yeah.
what is the unit of the vertical axis of the top to bottom values?
I don't understand.
We are talking about efficiency, but we see values from 100 to -600.
Oh, this is because we achieve higher voltages that it's allowed. So this is we should to stop the voltage here, but it goes further. So never mind. We should stop here. So this is the power of element. This is the mistake, because we go with the excitation of the voltage higher than the elements. It can be achieved. Okay, it shouldn't be here. We should stay up here. Okay.
So vertical axis is watts.
Okay, I will finish it. I should. I don't know why it's go to the 60, because it should stop at 50. Okay, let's try this one. I don't know why it's going further than we've got 50 at the maximum. But let's say we destroy this one. Okay, that's better. So that was, yes. That was the, where is this? This is the correlation between voltage and the current. Yes. Can you see it? This is the yes, this is voltage current, and this is the power of element. So we multiply voltage by current. So this is the power of the element. So here we should have the highest efficiency of these elements. Yes, because otherwise we lose something. Yes. So the problem. So this is the problem. The problem is to be here, even we change the light emission, yes, because we changed the light emission, so we moved a bit. So we have some tracking elements, tracking modes to find out this point, is this maximum point, yes. And back into our case, here are some, yes, this is what I said. So we've got the maximum power, maximum efficiency for the light, 100% light, and if the light decreases, the curve is moving, so the point also is moving. So we've got some. I would like to show you some slide, but I can't find it. Okay, this is. So we've got the maximum efficiency factor. You know, this is the maximum efficiency of the element. It's typically, this is the electrical, of course, this is the electrical efficiency, but typically the photovoltaic cells have the efficiency at about 10, 12, 15%. So only this amount of light energy we can transfer to the electric one, okay? But if we have this problem that we have no possibility to transfer all the light energy toward electricity, we need to be in this maximum point of the efficiency. So we should stay in this point. So this, we've got some tracking procedures to to stay in this point. Okay, what else? So if you can see, we can produce this photovoltaic panels with different substances. Yes, this is typical germanium, typical silicon, but we can also utilize different materials. If we utilize different materials, we've got higher band gap. So we achieve higher voltage on one piece of the solar cell, so we can use smaller amount of pieces to produce the element. Also, the different substances are sensitive for the different wavelength. Of course, we know that shorter waves have higher energy, so it's better to have the possibility to utilize the elements that produce the electricity from different waves. Yes, so it's better to use this kind of, better than the silicon that is just for 100 nanometer. Okay, and of course this is the different frequencies and different energies, because we've got different higher bands, gap bands. So we've got this allows us to produce more energy from one cell. Okay. There are two main, as a matter of fact, two main processes to produce solar cells. One is monocrystal and one is polycrystal. In the monocrystal, we produce a huge crystal. Yes, we produce a huge crystal, and then we cut them to the smaller pieces and glue them together, of course, electrically and mechanically. And another system is a polycrystal. We can produce polycrystal elements, and in this process we can prepare smaller pieces of silicon or germanium or crystallic element, and then we can glue smaller pieces together to produce one element, and then cut it and make a solar cell. Of course, all of both are similar conditions, but it's easier to produce polycrystallic, so they are a bit cheaper. I don't know, they are better or not. There are some, they are better because they have higher temperature coefficients, so they are, but they also can produce electricity from the light, the same as the monocrystal one. Okay, so I think it should be all for today. Do you have any question? Is everybody? Is anyone there?
Yes.
Okay.
Yes.
Do you have any question, or it is too much material?
We would have to think about it. So
Okay. I put the materials, the lecture materials on the website, so we will have the possibility to learn more and maybe discuss something more, or in the next lecture, or on the chat or something like this. Okay. So for today, it's all, as I said. So thank you very much, and see you next week.
thank you. Goodbye.
Thank you.
Goodbye.
Goodbye.
Thank you. Goodbye.